So I'm Jonathan. I've been working on Bitcoin for a while and been working on Lightning things for more recently, and I'm currently working at chain code on trying to improve like Lightning Network gossip side of the peer-to-peer network, because there's all the channels and all the messages involved in like sending a payment. Then there's all the messages involved in telling other people in the network where other people in the network are, because you can't route any payments if you don't know like the full state of nodes participating in the network and all the channels that exist.
Protocols.
I have spent some time doing like other related protocol work. There was some compression scheme for transactions over like the Blockstream satellite system, and Taproot assets as well, and like some DLC work. So yeah. This problem is interesting because well, first it's a bit easier to get things changed in Lightning than for like L1 Bitcoin, honestly. So it's like at least tractable that we could change like gossip P2P. But it's like kind of some scaling limitation that people don't think about often is just like resource use, not for the payment channels of like how fast we can send a payment, but all the like background resource use of like if we made the network 10 times bigger, if we start doing batch open and close of channels much faster, like what, not just will we use a lot of block space, but like will nodes be able to keep up kind of thing. So it's like a scaling constraint that I feel like doesn't get much attention of just like the networking, like how much data we have to move around to keep everyone in sync. The plan right now is there's an old paper from 2019, Erlay, that was like, oh, we can use minisketch, we can use this like really cool set reconciliation algorithm to exchange data instead of gossiping about it. So the plan is to just take most of the ideas from that paper and put them on Lightning. But there's a lot of differences because our messages are public and the Bitcoin like L1 messages are private. You're not supposed to know where they come from. So like our version of this problem is a bit easier. But right now I'm like running some infrastructure to collect data on like how the gossip network currently works. So I have like a system set up to be collecting a bunch of messages, and from there we can like do some analysis of like how quickly do messages get around, or like are there parts of the network that are missing messages, and ideally the patterns that come out of that collected data inform like how we design this replacement for gossip. So for the current status of like where I am with the project, I've got a lot of data. It's been about, I think we started running a big like portion of the infrastructure in February, so I've got like maybe 2 months of data. It's like I think half terabyte compressed or something, sort of compressed. So I'm starting to publish it for like other people to analyze if they want, because there's some other people working on this. And I'm moving towards more like simulation. Now we're like trying to mathematically kind of model, for example, like there's some patterns in the payment channel graph of like, there's different types of graphs, and there's like patterns where, you know, there's a few nodes with a ton of edges and then many nodes with like fewer edges, and this has like implications for, you know, what would happen if a big node fails, for example. Or like you can make arguments about like the network is this resilient because it has this kind of structure, but the P2P network is different because everyone's making like 5 to 10 connections by default, so it's like a very different structure. So trying to make arguments about that and then say like, okay, everyone's 3 hops from everyone else, and like we could communicate in this pattern because the P2P network has this certain structure. So there should be a draft bolt up soon. But. Yes, well, there's interesting like data science questions along the way, and I'm not a data scientist, so if we wanted to demonstrate something, there's for example, there's like 11,000 nodes or so, and if you just wanted to get a sample of gossip messages, the first thing you would do is just say, I'll randomly sample. I'll randomly like, you know, talk to nodes and see what comes out. But that may introduce like some bias if you don't know there's like, you know, different types of nodes out there. Like maybe you're just randomly going to talk to a bunch of nodes that don't have any information, and like maybe you want to do something else. There's a related problem of just like community structure. So like, hold on, let me try and draw something. something like this. There's like this graph problem you often approach of like, where are communities, or like, is there a way to kind of organize or think about this graph in different groups, and does that like reveal anything about the graph itself? So if you had a graph like this, one thing, if you wanted to just ask like, where are the communities here? Is there like any structure? One thing you could say is like, these three components are like different communities, and maybe that like means something. Like maybe these people all know each other, maybe they're all the same type of business or so. So this is like a heuristic associativity, I think, of like strongly connected components. But there's like a alternate interpretation of just like, this group is a community, and then these two groups are their own communities. So there's like a community of like well-connected people in the middle, and then other groups. And this gets weird. This is important if you're deciding which nodes to connect to sample data. So like, let's say the payment channel graph looked like this. Which interpretation would you pick? And that would give you like different results, basically like some different intuition about what's actually going on. This gets, like, you can imagine weird graphs where like, okay, now we have more people out on the fringes. Are these like three people, their own community? Are they part of these like components, or is there like, there's a bunch of different algorithms and like techniques to try and explore community structure. So I spent a lot of time looking around at that. There's some really cool techniques like structured block models of like trying to figure out structure without having some bias from the algorithm you're picking for this. So that kind of stuff's been fun. Well, I found a lot of weird stuff. So actually when I was collecting data at first, I didn't know what I would exactly be looking for. I just had some metrics in mind because there's some prior like papers and prior work on this. But it is helpful in deciding what anomalies to ignore. So there's like, for example, one big, of the like 12,000 nodes, there's like 2,000 nodes. That's this like weird project where they like sell hardware that you're gonna be running a network, but it's like two central nodes and then like 1,000 nodes hanging off of them. And they're like very clearly their own community off to the side. And like, they have like some certain anomalous behavior that I'm like not going to consider in terms of trying to address this gossip problem, because they're sort of doing their own thing, like not kind of in the core of the network. So there's like, I guess it also is helpful to look at like who to talk to, or like which, maybe there's like more central nodes that I didn't know about, and can look at their propagation, for example. I know there's been like cross-implementation propagation issues.
What does that mean, like cross-implementation?
So normally it means like, for example, an LND node that's surrounded by LDK nodes, or like there's 4 implementations, right? LND, LDK, Eclair, and Core Lightning, I guess. And like there can be situations where they have bugs in exchanging gossip messages. So like, you know, some nodes surrounded by nodes of a different type, generating messages and they're just not getting out, like they're not propagating farther. But if you like start to have some mapping of the, like how nodes are laid out, it can be useful to see like, okay, this pocket like does something different, maybe should look into like what messages they're producing, or just talk to them and see like what they're doing. Maybe they have some interesting behavior they've been observing. For what's next, I guess, I don't know. I have a very long delving thread that I need to update. There's yeah, it's mostly, I'm gonna start, there's some improvements to the minisketch library that I would like to look at, or like need to start benchmarking with that a bit, because the way that it was proposed to be used for Bitcoin L1 is like with quite different parameters from the way that I think it'd be useful for Lightning Gossip. So there's like, yeah, some specific parameters you need to pick to use minisketch, and like, I just need to test that and make sure that things aren't like absurdly slow. Well, if we're asking about will minisketch slow, I think it's possibly one of the best tools we could use if it isn't too resource intensive. I mean, we can draw out the problem if you want, but sure. So, or the framing of the problem. So in the graph we had before, it was just what we have now is we just batch messages every 60 seconds and then like send them to all of our neighbors. That takes a lot of resources. That's not, it should be obvious, but like so like the set reconciliation problem generally would just be like these two people have different messages. Eventually you want them both to have the same set of messages. How can you do that? With minisketch, the amount that you end up communicating between these two people is like, I guess, information, like theoretically minimal, in terms of here they have, what, 4 differences? If they communicate like 4 times some number, like 64 bits or so, they'll be able to recover the short IDs of these differences. So you'd say like A, and then you have totally unreadable. You have some message that may be any size, and then a short ID. For the original Erlay paper, this was 32 bits. For Lightning, it's probably going to be bigger, because the ID will be like public, but much larger. In the Erlay paper, it was private ID and much shorter. And that just meant that minisketch performed a lot better, because this ID was shorter, and it's like one of the key parameters for this. But yeah, there's a bunch of algorithms on like how do you get these people to end up with like the same set of information after you've run this like reconciliation protocol. And minisketch is just a very good option if you don't have too many differences. So there's like something, another parameter you choose is like how often are you going to do this reconciliation? You know, if I do it more often, maybe the differences each time are pretty small and like this actually works fine. If I do it too infrequently, these differences stack up and then this runs really slowly, and then actually maybe this is not saving us a lot of resources. So it's like another thing to tweak. But yeah, my system is using a fork of LDK node, so I'm mostly exposed to like developments on that side. But there's some cool progress in like doing mobile nodes that are really light, or like yeah, either using like block filters or like other more interesting instructions for like light client work. So I think there's cool work there as well.